Hello everyone and welcome back. In the previous session, we were introduced to the 8085 microprocessor. There, we tried to understand the word length of the 8085 microprocessor. From this session onwards, we are going to learn about the pins of the 8085 microprocessor. And today, we are in the part 1 of this series. So without any further ado, let's get to learning. Coming to the topics that we are going to cover in this session. Today, from the pin diagram of 8085 microprocessor, we are going to cover the pins 1 and 2. Then we will learn about the pins 3 and 36. Thereafter, we will learn the pins 4 and 5. And finally, we will also learn about the pins 6 to 11. So let's begin. Now, Intel 8085 is fabricated as a 40-pin DIP IC. Now here, DIP stands for Dual Inline Package. It means that the package is going to have pins on only 2 sides and 20 on each of the sides. Notice pins 1 to 20 on one side, and on the opposite side we have got the pins from 21 till 40. So this is Dual Inline Package, that is, we are having dual or 2 sets of 20 pins in this microprocessor. Let's now learn about the pins. We are going to begin our discussion from the pins 1 and 2, which are called X1 and X2. Now, whenever we are buying a modern day electronic gadget, be that a laptop, a PC, or even a smartphone, you probably have heard about the frequencies like 2 GHz, 3 GHz, 4 GHz and all. Now these frequencies, which I just mentioned, are nothing but the component which operates the microprocessor of the devices. If we specifically talk about the 8085 microprocessor, let me explain what happens in here. Generally, a piezoelectric material, that is a crystal, which is typically made of quartz, is used. Now these crystals have an ability to generate an electric charge in response to mechanical stress. Now, to this particular crystal, both the lines X1 and X2 are connected. Now, via X1, when the voltage is applied to this crystal, it undergoes the mechanical deformation, or if put simply, it vibrates due to the piezoelectric effect. And as the crystal vibrates, it produces an electric signal as its natural frequency. This signal through X2 is then used as the clock signal for this microprocessor. Now, specifically in case of 8085, the crystal within X1 and X2 has the natural frequency of 6 MHz. Now, via X1, when the voltage is applied, due to the mechanical stress, this crystal generates 50% of its natural frequency, that is, the output is going to be 3 MHz. And this means the 8085 microprocessor generally operates on the frequency of 3 MHz. So remember, the pins 1 and 2, or in other words X1 and X2, these are responsible for the clock pulse or the frequency of this microprocessor. Let's now talk about the next 2 pins, reset out and reset in. Now coming to reset out, that is the pin number 3, it is an output pin and it indicates that the microprocessor is being reset, which can also be used to reset the peripherals or the devices connected to the microprocessor. On the other hand, the reset in pin, that is the pin number 36, it is an input pin. Now reset in, as you can notice the bar on top of it, it is an active low pin. That is, if we apply the logic 0 to it, this is going to be activated. And reset in pin is used in order to reset the 8085 microprocessor. Generally, it sets the program counter to 0 and clears the buses. Now what do I mean by buses? These are all the channels through which the microprocessor can communicate with all the other peripherals. Now remember, these actions will be performed when an active low signal is given to the reset in pin. Now, in order to reset the 8085 microprocessor, the reset in pin should be held low for at least 0.5 microseconds. However, in practice, it is usually held low for a few milliseconds using a RC circuit or resistor capacitor circuit. So in short, reset in is an active low pin, which happens to be an input line, which is used to reset the 8085 microprocessor. On the other hand, the pin number 3, which is the reset out output pin, this is used to reset all the different peripherals connected to the 8085 microprocessor. Let's now talk about the next two pins. Pin number 4 is SOD, that is serial output data, and pin number 5 is SID, that is serial input data. The data transfer between the microprocessor and the memory or I/O devices can happen in two different ways, either serially or parallelly. When it comes to serial data transfer, SOD, which happens to be an output pin, that is pin number 4, is used for serial output. On the other hand, the pin number 5, that is SID, which is an input pin, it is used for serial input. Remember, these are the pins 4 and 5, which are used for serial output data and serial input data. Now comes the pins from 6 to 11. Now from 6 till 11, these 6 pins are used for interrupts. And that's the reason why we are calling them interrupt pins. Now before we try to understand about the interrupt pins, let me explain what basically is an interrupt. For an instance, say you are watching this session and at the same time you get a call. Now if it is an important call, you will have to take it, right? So using this instance, we can understand about the interrupt. If you think yourself as the processor, currently you are watching this session. So this is your main execution. And suddenly, if the call comes, you will have to pause this video and attend that call. Therefore, you will deviate from your main execution process and go to another execution process. That is, you will have to attend to the call. In this regard, the call is the interrupt. I hope the concept of interrupt is clear to you. Let's now understand about all the pins one by one. So we will begin with the pin number 6, that is trap. Now trap is a non-maskable interrupt. Now what do I mean by non-maskable? Well, whenever the trap line becomes high, the microprocessor will always have to attend to trap even if it requires the termination of the current process. You can relate to this by the example of the call itself. Say while watching this session, the call that you are receiving is to inform you that the results which you are expecting for a really long while is out. In that case, you are definitely going to attend the call, isn't it? So this can be an example of non-maskable interrupt. Anyway, for 8085 microprocessor, these interrupts are usually generated by the external devices. Generally, the trap interrupt signal is used for critical situations like power failure or hardware malfunction. And the vector address of trap is 0024H. Now what do I mean by vector address? Well, when the trap line is high, the 8085 microprocessor is going to address that particular interrupt. Now what should be done when the trap line is high? The instructions for that can be found in the memory location 0024H. This is called the vector address of the interrupt pin trap. So that's the interrupt pin number 6 or trap. Now we are going to focus on the pins 7, 8 and 9. That is RST 7.5, 6.5 and 5.5. Now unlike trap, these interrupts are maskable interrupts. That is, the microprocessor doesn't have to immediately respond to these interrupts, which was done in case of trap. Now coming to the RST interrupts, these are generated by software instruction. So generally, program developers can use these interrupts to handle different exceptional situations. Now coming to these 3 pins, RST 7.5, 6.5 and 5.5, they have different type of priorities. RST 7.5 has the highest priority. Then comes the number of RST 6.5, and finally, it is the RST 5.5. Now you must be wondering, what do I mean by RST? So RST means restart. Now why restart? Let me explain. I'll take the example of call once again. Say you have got a call while watching this session. However, the call is semi-important. So what you will do? You will pause this video for a while, attend to the call, then you may come back to this session, isn't it? So in that case, you are restarting the session. So when interrupts are generated via these pins, the main execution is always going to restart after the microprocessor has dealt with the interrupt. And thus the name RST. In other words, the short form of restart. So I hope why these pins are called RST is clear to you now. Now comes the next question. What is meant by these numbers? Let me explain them one by one. We are going to begin with RST 7.5. Now if you remember, when we were discussing about trap, we talked about the vector address for trap. That is, when the trap line becomes high, what the microprocessor is supposed to do, the instructions for that were located in a particular memory location. And that's also the case for these interrupts. In case of RST 7.5, we are going to take the value 7.5 in decimal. With that, we are going to multiply 8. Now, if we multiply 8, it will become 60. Now, 60 in hexadecimal is going to be 3C. And this particular value will be appended with 2 more zeros to the left of it. And now this will become the address where the instructions for the interrupt RST 7.5 is going to be stored. Similarly, for RST 6.5, if we take the value 6.5 and multiply 8 with it, we will get the decimal value 52. If we convert this to hexadecimal, it is going to be 34. Now in the address 0034, we will find the instructions which will help us deal with this interrupt RST 6.5. Similarly, for RST 5.5, with 5.5, if we multiply 8, we will get the decimal value 44. Converting that into hexadecimal, we will get the value 2C, and in the location 002C, we will find the instructions which will help us deal with the interrupt RST 5.5. Now I just mentioned these are generated by software instructions. So clearly, the software developers will also have to define how to deal with these. So let me explain the organization considering the RST 7.5 interrupt. Now as I told you, the instruction for the RST 7.5 interrupt will be located in the location 003CH. Let's consider the memory. So in the location 003C, at first a jump instruction is going to be stored, and thereafter in the next 2 bytes, a 16-bit address will be given. Now notice, this 16-bit address will be provided by the programmer who is going to use the RST 7.5 interrupt in his program. Now notice, we are talking about 16-bit address, right? Now if you remember, the word length of 8085 is 8 bits. Therefore, all these memory locations, they have the capacity to store 8 bits each. Now in order to store a 16-bit address, we are definitely going to use 2 different memory locations, isn't it? Now coming to the last address, that is 003F, here the instruction return or RET will be stored. Notice, using this particular instruction, the microprocessor is going to return to the main program. So, this instruction is going to help with the restart. So clearly, for RST 7.5, from the location 003C, 4 bytes will be occupied in order to store all these informations. Now let me explain how this all will play along. Say we have got the main code, and within the main code, the developer at certain point of time has written the instruction RST 7.5. Now during the execution of this, if RST 7.5 interrupt is generated, that is, if the pin number 7 gets high, in that case, from this instruction, we will come to this location. And why so? With the help of this particular calculation, the microprocessor will already have calculated the starting address of the instructions which will help us deal with the RST 7.5 interrupt. Now, as I told you earlier, this 16-bit address will also be provided by the developer. Now, this is the actual address from where the code for interrupt handling will be written. And the developer himself is going to customize this code for interrupt handling, which he has expected to be generated at RST 7.5. So let me explain the process once again. The main code is going to be executed, and at a certain point of time, if RST 7.5 interrupt is generated, the processor will go to this particular location, and this location will be found by the 7.5 notation, like we did in this case. And from this location, we are going to jump to this particular address, which is the starting address for the code for interrupt handling, which will also have to be created by the developer himself, expecting that the interrupt might occur. And once this is dealt with, by the end it will come back to the last address, and from this location, executing the return instruction, the microprocessor will go back to the main code. In other words, the main code's execution will get restarted. And this is going to be same for both RST 6.5 and 5.5. The only difference is the priority of RST 7.5 is actually higher than 6.5, which has the higher priority than 5.5. So that was all about the pins 7 to 9, that is RST 7.5, 6.5 and 5.5. Do remember, these are maskable interrupts. That is, unlike trap, the processor will have to generate something, which we will talk in some time, in order to attend to these interrupts. Let's now talk about the next pin, that is the pin number 10 or INTR. Now INTR actually stands for interrupt request. Now this is another maskable interrupt, and it has the lowest priority. This is generated by the external devices like keyboard or mouse. Sometimes, in order to interrupt a course of execution, we may generate some interrupts from these devices. And those can be generated using the INTR request or the pin number 10. And do remember, INTR has the lowest priority among all these interrupts. Let's talk about the last pin, that is pin number 11. It is called INTA, and as you can notice, due to the presence of this bar, this is an active low output. That is, via this pin, if 0 is propagated, that will mean it is activated. Now INTA stands for interrupt acknowledgement. Now if you remember, apart from trap, whenever we spoke about all the restart interrupts, including the INTR, I told you these all are maskable interrupts, right? Therefore, in order to service these, the microprocessor at first will have to generate INTA, that is, it has to acknowledge the interrupt, and then only these interrupts can be serviced. And that's the importance of INTA or interrupt acknowledgement. So that's all about the interrupt pins. Remember, interrupt pins are the ones which are from 6 to 11. At 6 we have got trap, 7, 8, 9 are the restart interrupts. Then as the pin number 10 we have got the interrupt request pin, and finally the pin number 11 is interrupt acknowledgement, which happens to be an active low output. So in this session, from the pin diagram of 8085, we covered the pins 1 and 2, basically X1 and X2, which are responsible for the frequency of the microprocessor. Then we talked about the pins 3 and 36, basically the reset in, active low input and reset out output line. Then we talked about pins 4 and 5, serial output data and serial input data. And finally, we learned about the pins 6 to 11, which we call the interrupt pins. Alright people, that will be all for this session. In the next sessions, we are also going to learn about the different pins of the 8085 microprocessor. So I hope to see you in the next ones. Thank you all for watching.